Hello, I'm Noor, and today I'll be giving you my master's thesis defense presentation. It's about autonomous UAV-UGV robot collaboration for the exploration and mapping of unknown environments. I did my master's at Ontario Tech University under the supervision of Dr. Scott Knockleby. To give you some quick background on my research, I'm using unmanned ground vehicles, or UGVs, in order to explore and map an unknown environment. This is a common problem in robotics and can be applied to a variety of different situations. So here you'll see this ground vehicle in this unknown environment, and it's able to use its sensors in order to navigate around the environment and to create a map of the entire area. Challenges exist within these types of algorithms. Although they do exist, one limitation is that using this 2D LiDAR, there's certain types of obstacles that cannot be detected, and this can cause the UGV to get stuck or damaged and unable to complete its mission. The second challenge in this area is the autonomous coordination of multiple UGVs. If we had multiple robots doing this exploration task, a larger area could be explored. It could be explored faster, which could be critical in certain search and rescue scenarios. And so it's desirable, although it is complicated, to do this in an efficient manner. On the second point of the autonomous coordination, it has been done in the past by a few different sets of researchers. This is an example of being able to have multiple ground vehicles and allow them to explore different areas of the environment so that it's performed in an efficient manner. And so such methods do exist, but there is a key problem. It requires the starting poses of the various UGVs to be entered manually. So this would actually look like an operator placing these robots, measuring the offsets and position and orientation between them, and then plugging that information into a program before it could be run. As you can imagine, it severely decreases the autonomy of this system, which is supposed to be fully autonomous. And so I'm tackling this problem by introducing a UAV into this multi-robot system. The first thing that this does is that it's able to detect the UGV starting poses, and this can initialize their global map and remove that need for manual human entry. And then the second thing it'll do is that the UAV will detect these obstacles that exist in the environment and that the UGVs can't detect themselves so that they could be avoided. Quick background about the robots. The UAV is a custom-built quadcopter, which I put together. It has its own computer on board, which allows it to fly autonomously and do some simple image processing tasks. It uses the robot operating system, so do the UGVs, so that the robots can communicate with each other over the wireless network. It has a camera that can also capture depth imagery facing down towards the floor. And since there can't be GPS in the indoor lab environment that I'm using for my experimentation, instead an external vision system is used for the UAV's position estimate. Yep. And then the UGVs are the Turtlebot 3 burgers. They're a kit that uses the Raspberry Pi microprocessor, and they're equipped with a 2D LiDAR. First, I'll be talking to you about the UAV-UGV localization method that I've created. Existing methods in order to localize multiple robots or UGVs and UAVs do exist. They usually rely on one robot visually spotting the other with some type of visual cues. So this could be like feature extraction or existing marker libraries. There's also a few other methods. The method that I went with is the use of the Aruco marker library. And although this has been done before, where the Arucos are placed on the UGVs to be spotted overhead by the UAV, existing methods have limitations because they require the UAV to track over and see the UGV by its Aruco marker during the entirety of the mission in order to keep its position estimate. I wouldn't want to do that because I want a scenario where we can have multiple UGVs to one UAV, and so we can't constantly track over them. The way that I tackle this issue of not being not it being necessary for the UAV to constantly track over the UGVs, can be shown here in my transform diagram. So what this shows here is that at the start of the mission, the UAV has its position estimate using the external vision system, like I mentioned, to this global reference frame map. Everything should come back to map. However, the UGV right now, and the multiple of them, are completely untethered and don't know where they are in space. So the UAV performs its flight to survey the area, and then once it detects its Aruco marker, now we can calculate the transform of the UGV back to the map frame and publish it here as a new transform. And then from this point on, its initial pose is always statically captured, and then its pose as it moves away from its initial position is captured using existing odometry and scan matching techniques. And so once the UGV has been found, it can do its thing and traverse around the area and still know its position relative to this map frame. This is a quick just showing of how, because of this 10 centimeter offset, when we find the Aruco marker using the camera, we must calculate back to find the center of the UGV using some simple math. And here's an overview of the relative localization method. So at the start of the mission, the UAV begins its autonomous flight, running the Aruco detection library, and then that Aruco information is put into this UGV localization node. This is the part that I created. And then the output of that finds the UGV poses, allows us to merge the UGV maps, start that global map, and then be able to thereafter start the autonomous exploration task. Looking closer at the UGV localization node, which I created, a quick overview of it shows how the Aruco information is captured in gathered into an array, and the reason for this is we want multiple readings in order to take the mean average of them in order to have a more accurate position estimate. Here I have that there must be at least 10 readings and allow for a 5-second window in order to kind of gather more readings so that when the average is taken, it's hopefully a bit more accurate. And so the UGV position is then estimated, and the transform, as was shown in red on the previous slide, is broadcast, and the ROS parameters for map merging can be set. And we're off to the races. Now here are my experiments for this method. Naturally, the first experiment that I would want to do is to measure the error in the UGV pose estimates as created by this method. So here the UAV flies over the UGVs in order to get readings of their Aruco markers and to estimate their positions. And then this is compared to ground truth, which in this case was coming from the external vision system available in the lab. This is the position estimates over one run. So this shows in blue squares the individual pose readings, and then the orange circle represents when the average of them is taken. And this is found to be quite close to the true pose, so it's a good result. You might notice in this graph, and then this shows it better over time, that the X error is pretty small. It's pretty narrow, but in the Y there's a lot more error and a lot more variance, and this just has to do with the path of the UAV over the UGV, the direction that it travels in. But when we take the average of them, we do get a good result. Over 10 runs now, the average error in position was found to be around 4 centimeters, and the average error in orientation was about 1.7 degrees. This was found to be a satisfactory result because for the map merging between the various UGVs to work, there should be a maximum error of 10 centimeters and 5 degrees. So we're well within that range with all these trials. So the experiments that I've been doing so far have been with the UAV flying at a height of 1.25 meters, and it was desirable to see the way that flight height might affect the accuracy of those pose estimates and its ability to track the Aruco marker. So it was found that when repeating this experiment at different heights, the error increased linearly with the flight height, and the variance also increased. Although even at 2.5 meters flight height, which is the maximum that could be safely achieved in the indoor lab environment, the maximum position error was still under 10 centimeters. So still a pretty good result at that stage. Finally, this is the global map experiment. So the purpose of this is to actually validate this multi-UGV localization method. So in here, the UAV would fly over this environment in order to find the UGVs. There's also been these walls set up in the environment, so the UGVs, LiDARs can see certain walls. So before the experiment was undertaken, Figure 19 shows the way that at the start of the mission, the UGVs, when they weren't placed properly, they didn't know where they were relative to each other. Their LiDAR scans did not overlap and did not properly show this physical environment. However, in Figure 20, after this localization, when the UGVs are placed appropriately, now their LiDAR scans do overlap and show the environment. I'll be moving now on to the obstacle mapping method. The goal of this is for the UAV to scan the area for obstacles and to share their locations with the UGVs, which is now possible because they have a shared map. Existing approaches to do this I found to fit into three main categories, which were elevation mapping, wherein the UAV performs a flight over the area, creates a digital elevation model for the UGV to then find a safe path through. Semantic segmentation, which is a machine learning approach that uses a convolutional neural network in order to classify each pixel in an image with the classifications such as like road, grass, vehicle, vegetation, etc., and then find a safe path through. The third category of methods I call discrete obstacle detection. And in these methods, I found that all of the approaches were limited to the obstacle needing to have a certain set color, geometry, or unique marking on it, which really limits their use in the real world where we might have obstacles of unknown features, right? So I found this to be an interesting gap for me to explore a little bit further. The way that I chose to approach this is by using the depth camera on the UAV. We're able to create a point cloud, which is a digital representation of three-dimensional space. This point cloud can be taken and then used to find the obstacles in the scene. So I've devised a series of steps for obstacle extraction where we take in the raw point cloud, put it through some steps, and in the end we should get just the obstacles in the point cloud. I'll show a demonstration of how this works. So at first we take in this raw point cloud, and then we apply a pre-processing step of voxel downsampling in order to reduce the number of points and make subsequent steps run faster. Then I apply plane segmentation via the ransack algorithm. This finds the largest plane in the image, which would be the floor, and then ignores all points within a certain threshold of that because the floor is not an obstacle itself. You'll notice some points here still bleed through, and this has to do with error from the camera when it's looking at the floor, error in the height, and it's seeing some points as above or below the floor, and I'll address that a little bit in my next few slides. But the way that I dealt with this is to be able to filter out these points. So first I apply a dbScan clustering algorithm, which just groups together points by proximity. And then I removed all clusters of points that had fewer than 50 members in my filtering step. And so this removed those very small groups of points that aren't actually obstacles, they're just caused by the sensor error. And then finally, we don't want to consider the UGV itself as an obstacle, and so it is removed from this obstacle point cloud as such. And so now we have our final output point cloud, which has only the obstacles in the scene and nothing else. Going back to this plane segmentation threshold, when we have the camera that I'm using, the Intel RealSense, looking at just flat ground, we can see in figure 28 that where the pixels are colored with intensity, height, and the z-axis, that there are some variations in height that's seen just looking at flat ground. From the highest to the lowest point in a single still frame, we can have a range of 6.6 centimeters. This is a result of the hardware being used. And so now when we're looking at objects ranging from 1 to 4 centimeters tall, we can see the 1 and 2 centimeter tall objects blend into this existing noise in the environment and cannot be reliably differentiated from the floor. This is a limitation of the hardware and not the method that I've devised. If we had a better camera or sensor available, then we could be able to detect even smaller obstacles. But at this stage, only obstacles that are 3 centimeters and taller can be detected. After we have our obstacle point cloud, we want to communicate these obstacles to the UGVs so that they could be avoided. The way that this is done is that I looked at the way that the UGV already finds obstacles using its LiDAR, wherein once it sees something in its environment with the LiDAR, it adds it to its cost map, saying, this is an area that I want to avoid. And so what I did here is I added the point cloud of the obstacle as an obstacle observation source. So it's another way that things get added to the cost map, and so now it has this pink glow around it telling the UGV to avoid that area. This highlights another strength of the method that I've created, which is that the obstacle's actual true shape is captured here rather than just approximating it as a circle or a square, and this means that the most efficient path planning routes could be used. And finally, I have my obstacle mapping experiments. Similar to the UGV localization, the first experiment had to do with using the UAV to track where obstacles were and to compare that to a ground truth to determine the error in the obstacle position estimate. And so I found the average planar error to be around 3 centimeters. When we take in the kind of inflation, that pink glow of the cost map, this shows that the UGVs will be able to safely avoid any obstacles found using this method. Another experiment was to find the robustness of this obstacle detection method. So the UAV was flown over a series of obstacles ranging from 1 to 10 centimeters tall, and it was found that all obstacles except for the 2 centimeter obstacles, 1 and 2 centimeter obstacles, were found reliably. They were found very quickly upon sight, and so this is what we expected. And there were also no false detections. The speed of obstacle detection I determined was to run at a rate of 7 hertz. So this means that 7 times per second the obstacle is taken, gone through all the steps that I devised, and the obstacles are extracted. So this means the UAV would be able to fly quite fast over the environment and still be able to pick up all the obstacles. Now moving on to the full system experiments, these best show kind of accumulate my research together and demonstrate what I've done. So I'm very excited to be showing this. We demonstrate both the localization and the obstacle mapping methods with this experiment. Here the UAV takes off and it performs an autonomous survey flight of the environment, going through a series of waypoints that I told it to go to, and what it's doing here is it's looking for the UGVs via their Aruco markers, and it's also looking for obstacles in the environment. All right, so now looking at the results of the relative localization method show us that the 3 UGVs were captured and they were placed appropriately in their environment in order to represent the space. So that's a good result. And secondly, the obstacle mapping shows that the 3 key obstacles that were placed in the environment were also located. Here we can also, now showing the cost map, highlight that if there was no obstacle detection, the UGVs would have never known about these key obstacles around them that would influence the way that they could autonomously explore the area. This shows the UGV mapping process where the UGVs traverse amongst the area and in order to create a full map of it. And now we can look at the final results of that and see that this final map does accurately represent the environment that was created. If you might notice these stray points on the outside, that is caused because of these barriers that were created for the walls being very narrow, and sometimes the UGV LiDAR is seeing above or below it. But if there were solid walls, we would have a cleaner result. And any warping that's seen in the map is not caused by my methods, but only inaccuracies in the existing methods for UGV localization in terms of the scan matching and odometry. Yeah. Okay, so in conclusion, my contributions have been the development of a novel method for UAV-UGV relative localization using the Aruko markers, and then secondly was the development of a novel method for UAV obstacle mapping for UGV avoidance. And in this scenario, these two methods were applied to the exploration and mapping task of an unknown environment, but they can be used for a great variety of missions because anytime you have multiple robots working together, there needs to be some form of relative localization, and similarly, obstacle mapping and the concept of the UAV being able to share information with the UGVs can be applied to a variety of mission types as well. Recommendations for future work. Some ideas that I had which could be improved upon was to update the UGV poses mid-mission with the UAV data. So what this means is right now the UAV is only looking at the beginning of the mission to find the UGVs, but maybe halfway through or during the mission it could also look for them to correct any errors that might have accumulated in their odometry. Secondly, something different from Aruko markers could be used, and this would help for Aruko markers don't work so well in like unstable lighting conditions or dim lighting conditions. So that could help. And finally, the methods that I've created, particularly the obstacle extraction, only function in 2D environments, so some changes would have to be made in order to apply it to a 3-dimensional space. These are my publications. These are my references. Thank you very much for listening. I was presented this defense on April 5th of this year, and I was very happy that my defense and my thesis were accepted by my committee, and I'm able to move on and to graduate. I had a really good questioning period with my professors that lasted for 40 minutes, and that was very interesting. But in the end, I was successful in my defense. I really appreciate the support that I've gotten from my friends, my community, my lab members, Dr. Knockleby, throughout my thesis, and I'm very proud of what I've accomplished. All right, thank you for hanging on for 22 minutes with me. And if you want to see some bloopers I've included in my extra slides, I don't know why there's 2 of me now, but here's my blooper reel. Tragic. All right, adios.